Hello everyone, my name is Mecca Evans and this is my final project for ISAC-317. I've created a smart LED notification home system which is designed to provide visual, non-intrusive notifications using color LEDs with a Raspberry Pi 4B. The system is effective and it also provides a solution to communicate important status updates such as system health reminders and connectivity issues within your device. This is the GPIO pinout chart I'll be using for the breadboard. Here I am just updating my Raspberry Pi and updating my system, making sure that everything is running smoothly before I attach my breadboard to my Pi and I start testing things out. Next, this is my breadboard and my Raspberry Pi setup. I am using 5 different LED colors: red, yellow, green, clear, and blue, and I'll explain further what these colors represent. I will be using the physical pin setup for this. So blue will be on pin 16. Blue will represent the script startup. Red will be on pin 11. Red represents a warning or a critical issue. Yellow will be on pin 13. Yellow represents a pending issue. Green will be on pin 15, and green represents a healthy system. And lastly, white, which is on pin 18, will also represent a healthy system, saying that things are all clear and all ready to go. I did run into a few issues when updating Python, but that's okay, I got it fixed. Now it's time for the test. As I said before, the blue LED does represent startup of the Python script. So when the Python script starts, the blue LED light will remain on for 5 seconds. Then it will go green and clear to show that the system status is healthy. Next, I will be demonstrating turning off my wireless network, which will create a red critical warning issue because the Wi-Fi is down. Then I will turn the Wi-Fi back on using this code, and the green and clear LED will turn back on to show that the system is up and running and the Wi-Fi is actually working now. See, there you go. Next, I will be putting a stress on the CPU to show that there is a pending issue. Right here, I'm going to use stress CPU 4 for this one. As you can see, the light did change to yellow, from green and clear to yellow, showing that there is an issue, an upcoming issue. Once you cancel that CPU stress, the lights will return back to green and clear, which suggests that everything is healthy and all clear. I will be stressing the CPU again at a level 2, just to show that even at a level 2, the light will still turn on, showing that there could be a pending issue going on with your Raspberry Pi. And the light should change. There it goes. Lastly, this is one more good look at my breadboard. You can see how I have everything connected properly. My resistors are connected to my LEDs properly, and my ground is connected, and everything looks good. And I had so much fun doing this project, and I wish the best of luck to everybody. Bye.
Hello, my name is Meg. My project is the moisture sensor device for plants. Just as kind of an introduction, one problem I've noticed is that most people who have houseplants usually either overwater their plants or underwater their plants. Both of these obviously cause issues. Overwatering can cause like root rot. Not watering your plant enough will cause it to dry out and die eventually. So there are some solutions for this right now. One that's really popular I've seen is just like apps that send you a notification when after a certain amount of time has passed since the last time you watered your plant. I've used these and they can be helpful, but they're not always the best just because they don't know like your environment's humidity levels or temperatures, that kind of thing. So sometimes even with those apps, you'll still end up overwatering or underwatering. So my goal was to use sensors to tell you exactly when the soil within the plant is dry so that you can water it then. The materials for this project is a Raspberry Pi, the power supply for it, a micro SD card with the Pi OS downloaded, some jumper wires, the moisture sensor, and the potted plant to test with. The sensor has three pins to be connected: the positive power supply pin, the ground pin, and the digital output pin. And those are visible there. To set up the Pi, it's connected to power and that SD card is plugged in. And then I had to wire the sensor as it was mailed to me. It wasn't connected, the sensor itself, to the probes. So that was pretty simple, just kind of plugging it in. It has two pins and it doesn't matter which side it goes into. So basically just plugging it in there. And then I wanted to make sure that the pins from the sensor to the Pi are in the right places. So the VCC pin of the sensor goes to pin 1 on the Raspberry Pi, or the 3v3 pin. The ground pin goes to the ground pin on the Pi, which is pin 9. And then the digital output pin goes to pin 11 on the Pi, which is the GPIO output 17 pin. You can also test to see if the sensor is working just out of box. It's got some LED lights on it that indicate whether it is reading like a positive, that there is moisture sensed or not. So if the light turns green and or switches from green to red, then that means that it is working. And I've got a demonstration. This is just the plant that I used. I've got that video here. All right, here is my demo for the moisture sensor. I've got my Python running through the Raspberry Pi that I'm remoted into from my computer. Just gonna run that. And then this is the sensor here. You can see that it's working with the LEDs. So this plant does have water in it, and then this one it does not. So to start off, the green light is on just because that one does have water. If I take that out, you can see that the output there has changed. Obviously, you can see the light there. And then it has sent an email saying that there's no moisture detected and it's time to water the plant. And then, so, okay. That one's really dry. Put it in there, and then when it's in the plant that does need to be watered, you can water it, and it should send another email saying, you can see the LEDs back on there, and the email has sent here, so it's all set, and it has been watered. You can see there. So the code was successful. It sends an email to the email account that I set up, as well as you can see um, the indications within the command line there as well. But in conclusion, I think that this kind of succeeded in improving upon the current solutions and kind of solves the issue of over and underwatering. I do think that the project could be improved if I had kind of more technology with the Pi and more time. I think some things that would work really well is if you had more sensors so you could do more plants. If they were like wireless sensors, like through Bluetooth, I think that would be really helpful just because I know I have a lot of plants and they're kind of spread out throughout my apartment. I also think if I had more hardware for it, it'd be really cool if it had automatic watering. So if it just was attached to like a reservoir and would automatically water the plants for you. But yeah, here are the references I used, and thanks for watching. Alright, here is my demo for the moisture sensor. I've got my Python running through the Raspberry Pi that I'm remoted into from my computer. Just gonna run that. And then this is the sensor here. You can see that it's working with the LEDs. So this plant does have water in it, and then this one it does not. So to start off, the green light is on just because that one does have water. If I take that out, you can see that the output there has changed. Obviously you can see the light there. And then it has sent an email saying that there's no moisture detected and it's time to water the plant. And then, so, okay, that one's really dry. Put it in there, and then when it's in the plant that does need to be watered, you can water it, and it should send another email saying, you can see the LEDs back on there, and the email has sent here, so it's all set, and it has been watered. You can see there.
Hi, so this is my final project for ISAC-317, and for my final project I decided to take a more software focused route and try my hand at web hosting. So I chose to use Apache 2 for my web server. I am really into indie web design and just independent, privately owned and hosted websites. So I thought this would be a pretty fitting project for me and one that I could continue to use after the class and continue to tinker with and hopefully host my own website. So before I got to do anything, I had to actually set up SSH and also VNC into my Raspberry Pi. I wanted to use VNC because then I could look at my Pi desktop as if, in a window, as if I was using a virtual machine. This just made it easier for me to explore files. Yes, there are commands for that, but I like to have the visual open in one window if I needed it, and then I didn't have to mess with cords and stuff. And then I used SSH to actually run any commands, edit the configuration files, set up the firewall, all that sort of thing. As for the actual configuration of the Apache 2 web server, which installing that is super simple. You really just run a couple commands to do that. But then comes the configuration. So some of the steps I took there were first turning off server tokens and server signature so that potential attackers can't just easily look at what type of server I'm running, the host I'm using, that sort of thing. We don't need to be giving them that information. I made sure that not just anyone could view the directory of the website. Then I changed ownership of the all the directories that were connected to Apache 2, which I probably should have done later so I didn't have to run a sudo command every time, but that's all right. So handing ownership to less privileged accounts is just good security practice in general. You're kind of not putting all your eggs in one basket there. I limited the protocols that would be allowed, limited to get, post, and head. I also disabled trace requests. And then finally, again, this step was probably a little bit out of order, but I was kind of focused on the configuration file first and then moved to other things. I installed Uncomplicated Firewall onto my Raspberry Pi. Very necessary step. Again, probably should have been earlier in the process, but I got that set up and set the rule to default deny all, just because for now this is just a private project. So I really don't need much extra going in there. I did allow communication with my host computer, but that's it. And then this is just sort of a quick, brief demonstration of obviously SSHing into the Raspberry Pi. And then in a moment here, I'm just going to quickly go through the configuration file, which, of course, that will also be attached, but I'm just scrolling through quickly so you can kind of see a couple things that I added. And then here, I'm just typing in the address in my browser to access the website and show that it's running. So there's the default one. I put all of my web files in a separate folder, or a subfolder, I should say. And here's that. I will say it took a little bit longer for my web files to load compared to what I'm used to, but other than that, I think it went pretty well.
Okay, so for my final project, I built a homebrew locking mechanism. Um, the problem I built this to solve was that many people are subject to theft in their homes, and there often is no way to know who the perpetrator is or when something is stolen from them. In my personal case, I have many belongings in my office and home that are borrowed without asking me for permission, and I want to know who is taking my belongings and provide a way to keep them secure. So to address this problem, I built a solution for that is a lockbox mechanism that has integrated features including a keypad for allowing input from the user accessing the lockbox, as well as a camera for taking pictures whenever someone enters in an incorrect password. In regards to building the lockbox and the parts required, I used a Raspberry Pi Model 4 with the power supply and all of the other peripherals you need for using it. As well, I used a 4x4 matrix keypad, which will be used for input from the person trying to access the lockbox. I also used a Pi camera module that's going to take pictures whenever somebody gets the password incorrect. And then for the lockbox mechanism, I used a solenoid lock that has its own power supply, which the relay controls the power going to it. So basically, the relay is used to unlock the lock. So moving on to solving the problem, the first step I took was setting up the camera, which was used a ribbon cable, and I just connected that to the Pi and did a test where I took a picture with it and everything was working. It was pretty simple. And then I made some code with that to test using Python to control the camera. So I would, because I know I would eventually be using it to take pictures once the lock is um, activated. Um, then I moved on to the keypad setup, which consisted of me connecting the 8 GPIO um, pins from the keypad, so it would have four for the rows and then four for the columns. And then I built a program for scanning the keys and basically showing which keys the user is entering. Um, After the keypad was set up, I moved on to um, setting up the relay for working with the Pi. And I did a test with a buzzer, so the relay would be turned on when I clicked enter and the buzzer would sound. And this initially didn't work, but after troubleshooting it did. And then after I set up this relay, I replaced the buzzer with the locking mechanism and the external power supply, which basically has it where the relay controls when the power supply is powering the lock, and when the lock has power, it unlocks basically. Then the last step was just to build a housing for the all of the wires as well as the camera and keypad. So I'm gonna go over the code configuration real quick, just a quick overview of everything. Here are some of the imports that I had to use for the project. It's for GPIO pins as well as the camera module. Um, I specified some of the camera settings and then moved on to specifying what the correct password is. Here we have it as 4523. I also made an empty string for whatever the user inputs as their password. The next part of the code is for specifying what the keypads are. Like, so I made a 2D list that has the layout of the keys, and then I moved on to making a function for the lock to activate. This right here has an output set for when the lock deactivates, and then when the output is set to low, the lock activates again. So utilizing that, I have it where the user key presses hashtag when they want to act as when they want to enter in their password, and then if the password that they entered is equal to the correct password, access is granted, and then that function that deactivates the lock um goes, and then if it's not the correct password, access is denied, and then a picture is taken and saved to a folder on the Pi. Um, there are some more there's some more code written for just cleanup and different cases of appending and acting as a clear key, but this is pretty much all that the code is going through. It's pretty simple, but I'll move on to the demo of the lockbox now. Okay, so here's the actual lockbox mechanism. It's housed in a cardboard box, but here you can see that we have the keypad for the user input, and then the camera for taking a picture of when somebody gets a password incorrectly. Then if we open the actual box a little bit, we can see that the Raspberry Pi is here in the corner right here, and that's connected to 8 of the GPIO pins for the keypad. And then we move on and you see the blue box there, which is the relay, which is used to control the output towards this lock right here, which comes out of the box and can connect to another box, which would actually be where your belongings would be housed. And there you see the external power supply being connected to the relay and the lock for connectivity. So now we're going to move on to demoing the actual box. So I'm going to start the program now. So right now it's initializing and it tells you to enter a password. So the correct password is 4523, but I'll be entering in an incorrect password to show the picture being taken. So right here I entered in the password 8936. So you can see that the pad is scanning. And so we're gonna click hashtag to enter in the password. And then here you can see that it says access denied, and then it will take a picture. I'll show it here. So that picture should be saved in our desktop and we'll check that after. But now we'll show the correct password being entered. So 4523, pressed all of those. Then if I enter now, I'll look at the lock mechanism. You can see that the lock deactivates and then activates again. So on the console, it will be the lock deactivating and then the lock activating. Just to show what the camera functionality looks like, it gets saved in a lockbox photo JPEG, and here you can see me gets saved in a lockbox photo JPEG, and here you can see me recording over the camera. And this just shows a demo of how the mechanism will work.
Hi everyone, my name is Zainab, and this is my final project presentation for a DIY smart home automation system using Raspberry Pi. The purpose of this system is to improve home safety and efficiency by integrating features like motion detection, environmental monitoring, and smart alerts. Although I didn't build the physical system due to time and hardware limitations, I simulated the entire workflow. Everything from sensor readings to notifications to show how the system would function in a real setup. In the next few slides, I'll walk through the problem I wanted to solve, the system design, what was simulated, and how it all ties together. So why this project? Commercial systems are known to be expensive and closed source. Most smart home systems on the market today are expensive and rely on proprietary platforms. That means users often have limited control over how their devices behave. There's usually a trade-off with privacy since the data goes through third-party services. I wanted to create something that's more affordable and customizable using open source tools, low-cost hardware, and code that the user can fully control. The idea is to empower users to build and modify their own smart home devices without being locked into a commercial ecosystem. The system is built around the Raspberry Pi 4 as the main controller. It connects to a PIR motion sensor to detect movement and DHT11 sensor to monitor temperature and humidity. LEDs are used to simulate smart lighting. On the software side, Python controls all the logic and sensor communication. Flask runs a local web app where users can see live data from the sensors. And SMTP is used to send email alerts when motion is detected. Kind of like a basic home security feature. Everything is self-contained, private, and customizable. So what's been simulated? Because I didn't have access to the physical hardware, I used Python to simulate the behavior of the sensors. I generated realistic mock data for temperature, humidity, and motion detection. The data is logged to CSV files, which then the Flask app reads to display on a web dashboard. I also set up the logic for sending sample email alerts. This helped me test how everything would work together and gave me a way to show how the system performs even without physical components. This slide shows some of the simulated data that was generated. Motion was randomly detected and logged at regular intervals to mimic someone walking into a room. The DHT11 sensor was simulated to report temperature and humidity every minute. I visualized this data in charts and logs, which could be viewed in the Flask interface. These outputs demonstrate that even in a simulated environment, the system works exactly as planned and would function the same way once connected to actual sensors. One of the biggest challenges I faced was obviously the lack of physical hardware, but by focusing on simulation, I was still able to create working model for the system. Python, Python and Flask made the process smooth, and the project is definitely scalable, meaning it could easily be expanded with more sensors or a mobile interface in the future. I learned a lot about the IoT devices, how they communicate, how to stimulate sensor data, and how to tie together a full system using open source tools. Overall, I'm really proud of this project, really proud of how it turned out, even without physical implementation.
Hello, my name is Jarrett and I'm going to show you my IoT CPU temperature aggregator. I have computers where the CPU may run hot and I'm not aware of it. For example, my media server CPU could get warmer when streaming videos, but I wouldn't know if I'm not in front of it. I want to know when they get very hot and log the temperature over time to see when they run hottest. Using a Raspberry Pi, I will aggregate system data like temperature and perhaps utilization. Optionally, I can log data with a temp humidity sensor attached to the Pi for ambient room temperature. This allows me to determine the delta temperature from the environment. The computers I want to monitor will have to run a background service or a routine script to feed or expose the data to the Raspberry Pi. I will show my code for the project. At the top of my Python script, I import all the libraries I use. The devices config dictionary is a configuration of what devices I want to have in the dashboard and record. Endpoint is the URL to Libre hardware monitor, to the data.json file, and the data.json file contains information such as temperature and system utilization. The gap time variable is the number of seconds it takes for data to be missing before it shows a break in the line graph. The refresh time is how many seconds it takes for the data on the dashboard to be refreshed in the browser. By default, it's 5 minutes. The refresh JSON function will request the URL that's provided. It's going to wait for there to be any errors, and it's going to catch if any of these HTTP related errors occur. And this was necessary in my environment because the Wi-Fi at my house drops every once in a while. So if I didn't properly account for this, it could crash the entire script. And if there's any issues, it's just going to print out what the error was and continue. The find CPU temp function parses the JSON data for the CPU or CPU package temperature, and then it strips out the degrees Celsius unit to make it easier to graph the data. The log to CSV function opens up the CSV file where I store the CPU temperatures, and it appends a new row with the time, the device name, and the CPU temperature. The print CPU temp function goes through every device in the configuration it's going to fetch the JSON from the endpoint, and it's going to load the JSON into this parsed data variable. It's going to eject the CPU temperature, and then it's going to log it to the CSV file. The run dashboard function uses dash and plotly to make a web server that will show the data in the CSV file in a line graph. It uses the pandas library to read the CSV file, and then it handles all of the rows data types. This line here calculates if the gap between two data points is exceeding the gap time, and then it's going to fill in with none data value, and this will create gaps. So there's not a line that's misrepresenting the rate of change. The collect data loop function runs forever, waiting a second, and then it's going to get the new CPU temperatures. The main function is going to create a new CSV file if it doesn't exist already, and then it's going to use multiprocessing to run both the dashboard and the data collection functions at the same time, and this reduces the need of having two scripts. My first attempts to use a virtual environment to handle the dependencies did not work out. It resulted in NumPy claiming the interpreter was run from the same directory as the source tree, which wasn't true. NumPy is a dependency of the pandas library. I tried using apt packages to install into the system-wide Python environment, but the dash Python module isn't packaged for Raspberry Pi OS. I tried using pipx on top of the apt packages, but the virtual environment pipx creates doesn't include the system-wide packages either. Since I had issues with NumPy importing, I opened up a Python interpreter window. Attempting to import it from there showed that there was an error that said libopenblas.so cannot open shared object file, no such file or directory. And then I saw that referenced in a GitHub issue comment. So I ran sudo apt install libopenblas-dev, and then I launched the script again and it imported without any errors. Next, I'll show you the dashboard. The dashboard shows two lines, and there's a line for each device I have added. You can see here is when I intentionally added stress to my CPU to make it show up on the chart. You can also zoom in, and you can see all of the data points that are taken every second. And this is what it looks like when there's a gap in the data. On the Raspberry Pi side, this is what it looks like in the script output. Thanks for taking a look at my project.
All right, how's it going? Here we go. This is Robert Stewart, and I'm doing the final project for ISAC-317. Let's see here. So this my problem statement was pretty much making a do-it-yourself thermometer. So here we go. We got the breadboard. I got the sensor, Raspberry Pi 4. All right. So the setup was to have each light was to represent. Oh, here you go. Each light was to represent 20 degrees of temperature. So 0 to 20, 21 to 40, 41 to 60, and so on up to 100. And then I was going to have this light be flashing if the humidity was above 90%. So here's the sensor, and oh, there you go. And it's powered on, it's working, but actually I didn't actually get this whole thing to work, so a lot of it's going to be simulated. Yeah, I got like the traffic light to work, and I pretty much followed the same setup, but yeah, we'll just go over the code and I'll like simulate how it actually worked. All right, so here we go. Up top we have the this is all the basic imports. I tried to use like a library at first, but I kept getting an error with the pipe3 command, like it's the add-a-fruit underscore DHT. Well, that was recommended with the sensors, but I just couldn't get it to install on my Raspberry Pi. So I went like super basic bare bones because I could like pretty much write this from scratch because I have a little bit of code writing experience, but I just tried to go super simple. So up here I have the lights set up for each right here. So like right here is like 11, or no, up here 11, 13, and 15, and down here is 29, 31, and 33, and those are my lights. All right, and then the DHT22 pin is 7, which is like up top. It's one of these. And then if you look on here, the sensor on the back, it has ground S, I think S is for source, and then VCC. I don't know what they mean, but each one has its own designated spot. And then I have them set up right here in proper spots. I use the pin out to make sure I had them in the right spots. All right, that's my cat going crazy. All right, and then next we have right here we set them all to false. Just like up here we have it's supposed to read the temperature, and then I got this part from online from like a tutorial. It said to like have this in there first to set like a temperature, and then it's supposed to read it, and I don't know, that's how it works, I guess. And so we set them all to false, so all the lights should be off. Here's my cat. Here you go. And then if the temperature, this would be like the main portion of the script. So if it's less than 20, the bottom light should come on. This one should come on, and then at 40 and so on. Yep. And there's like the temperature ranges right there. Here's a humidity section, which is again supposed to be for this top one right here. That's all on its own. I wanted it to flash if it was above 90. And then the try, or right here, the while true is just it's supposed to like read it and then send it back to the sensor, or read it from the sensor and send it back into the code, and that's how it updates itself. And then just the keyboard interrupt. And then to prove this, I was gonna, if it actually worked, I was gonna like have a boiling pot of water and then a bowl of ice, so you could actually see the lights change, like going up and down, and hopefully have the boiling water would turn on the flashing blue light for humidity. But it did not work out that way. Yeah, and then to go even another step further, you could add in like sending it online to like how the one of your examples had a website set up, so we could you could read it from that. But yeah, this is it. I mean, it looks right to me, at least. I don't really know what I'm doing. And then yeah, I think it looks good to me, but it's just not working, I guess. So I don't know. There you go. Have a good summer break. Take care.
Okay, hello. My name is Antonio Woods, and for my final project, I made a temperature reader with my Raspberry Pi. So we'll get started. So my problem statement, at first it was for hermit crabs, and it still kind of is. I just don't have any, but I also have been looking at pet triops, like pet shrimp. And either way, both of these pets require a very strict temperature. Otherwise, it can be absolutely fatal to them. So my problem is, most houses, including mine, have a thermostat where you can check the average temperature in the house, or what the temperature is set. But it's not always accurate, as in most of the rooms in my house, different rooms can have a different temperature. Just like my brother's room in my house, there's actually some kind of poor insulation in there, and so what's warm in here can actually be cold in his room. So I can't just walk downstairs and look at the thermostat when I need to know the temperature of the room that the pet is in, like the triops or the hermit crabs. So I need to make my own temperature reader for this specific room. And so that's why I'm making the temperature reader. Technical feasibility, my bad. It wasn't hard. It's a very easy build. All I needed was my basic Raspberry Pi, female jumper cables, my power supply for the Raspberry Pi, and then a DHT22 sensor. And that's it. So pretty much I had all of the parts before I even started this. I just needed to get the sensor, and that only took like 2 days. So hardware, everything came along just fine. And then I guess for software, needed use the Nano thing since this is Raspberry Pi uses Linux. Use the Nano editor to make a Python script. And well, before even that, the only software I needed was I needed Adafruit, like some Adafruit libraries, because that was supposed to be the only way I'd be able to for the DH2 sensor to read anything. So I had to install those packages onto my Raspberry Pi, and that was it. And then all I had to do was make the Python code. Solution design, well, as I said, I would just make a temperature reader that gives me the temperature that's currently in my room, because I can't trust the thermostat downstairs to give me the accurate temperature. So whether I just have the temperature up on my desk or up on my wall, as long as it's in my room, I'll actually know what the temperature is in there. Adherence to RILA. Now, I do have something or a little bit for each one. Of course, it's not like sophisticated, but you know, device integration. Device integration, I have the DHT22 sensor. Then I have all of the female jumper cables, the double head female jumper cables for the 3 pins on the sensor and the 3 pins on my Raspberry Pi. Those went, yeah. And then I needed the Adafruit Blinka libraries for the Python code to read the DH2 sensor. Device management. This consists of making sure my packages and system is up to date. So yeah, that's the only thing that I needed when it came to device management. I just need to make sure that my Raspberry Pi's packages and whatnot were up to date and were upgraded to the latest. And it's the Adafruit libraries that are imported in my code that will register that sensor data. So data management, that just consisted of me putting the sensor readings into Fahrenheit, because at first it was only giving me readings in Celsius, and you know, I think most Americans don't use Celsius. I know I don't, so I wasn't really understanding it. So I had to put in more code to change it to Fahrenheit, like convert Celsius to Fahrenheit. And I needed it to print out in a way that I can understand it. I'm pretty sure if I didn't have like any print commands or whatnot in the code, it would just look like a whole bunch of jibber jabber. So that was data management. Then context management. For that, I didn't do much, or I didn't need much. I just put a code where if it got below 72, which is not suitable for these pets, or if it got above 85 or a consistent 85, that's also not good. It'll just put an alert in the terminal when it's running. So yeah, it'll just be a big alert, along with all the other temperatures and whatnot. So thing integration, integrated it by, well, at first I could only view this Raspberry Pi on my one monitor for my PC, and it was kind of tedious having to go back from the HDMI display back to the display port. So I set up VNC Viewer, because obviously I can't hook my PC all the way up onto the wall or wherever I put this thing at. So I put VNC Viewer on my laptop where my laptop could just sit off on the edge of my desk and give off readings and whatnot. So I installed VNC Viewer, whatever I needed to on the Raspberry Pi, and then I installed it on my laptop. And I'm running out of time, but the steps taken, I'm gonna be brief. I had to get the parts. That's done. I only need the DHT22 sensor. The next step was to set up both the Pi and my laptop with VNC Viewer. That wasn't bad. Set it all up, and I hooked the sensor onto the Raspberry Pi with the correct pins. Step 3 was to make the actual code, and I'm not gonna lie, I'm terrible at Python, or I've never been able to learn and retain much information, so I need to get some help. I got some AI help from Chat GPT. I'm not that bad at Python, but I was just like, hey, can you take a look at this and see if it would blow up or anything, and it would just tell you what changes I need to make. So I did get some AI help with making this Python code, but I did do the Fahrenheit configuration part on my own, like the conversion. So yeah, so that was like step 3. Then step 4 was to test it, and that's in a different section. Code and configuration. So this is a brief look at my Python code. I'll probably show it in the following video after this, but this is the code here. And then this is the software that I needed to make said code work. So yeah. And now we're on to testing and validation, and that will be a second video stitched onto this one. So I'll be back. Okay, so we're back, and this is the final product. This is the temperature reader. We have the power supply, HDMI cord that hooks up to my display, keyboard and mouse. I'm just using an old keyboard and whatnot, old mouse, and then we have the actual sensor. The DH222 sensor has all the pins connected in and whatnot to their respective pins. So this is the final product, and it might look pretty, like, what's the word for it, messy, because it's supposed to be like remote, but I'm only doing this because I get a better picture on the monitor instead of as you can see over here, I actually do have VNC viewer connected. But yeah, all of this, like other stuff, wouldn't be on it if I was using VNC viewer, but I'm not for this video. So yeah, so there's the sensor, and now we go on to testing. So I have the monitor right here. This is the terminal, and now we're gonna test Python free DHT reader. Uh-oh. Well, at least there's evidence right there that temperature was not good for a second. But as you can see, there it goes. It's giving me not only the temperature in Fahrenheit, but also the humidity. And it gives me a new temperature every 5 seconds. At first it was 2, but then I changed it to 5 because I don't need every single second. Okay, so now it's on to the test. So it's not a long video. I'm just going to do a second test. So right now it's saying it's 75.7 degrees. Now I'm just going to blow on it with hot air to see, like, show that it changes and whatnot. So here we go. As you can see, not only did I blow hot air on it, but now I'm pressing my fingers against it, and it is going way up in temperature. Now it went from 75 to 76 to now 79 to 79.7. And the humidity, because of the air that I blew on it. So now it reached 80. So yeah, it's definitely working. Definitely working as intended. And so, yeah, I did an earlier test where I opened up the window, turned on my fan, turned on my desk fan, and I let the air get chilly, and it did in fact go down a lot to like 70. So I put that in the report. But yeah, this is my final project, and that's the end of this video.